Hello, today we're going to talk about some applications of the double integrals that we've been working with lately. In particular, we'll work with density and mass calculations. We'll have to start with mass, and I should say we're going to work with density and mass calculations and then center of mass calculations. And so it turns out that if we have some sort of, we call them laminas, but it's just like a very thin plate-like object, and it's got density in it that varies depending on where you are on the plate. And if we know a function that would model the lamina, and then we also know the density function, then we can use double integrals in order to calculate the mass of the lamina. So in this formula I have right here, this row of xy, that is going to be my density function. And dA is going to be coming from the shape of the lamina. And if we integrate the density over the shape of the lamina, we're going to come up with the mass of that lamina. So let's start with an example. We have a flat plate. It's in the shape of a region in the first quadrant that's bounded by x equals 0, y equals 0, y equals ln of x, and y equals 2. Okay, I'm going to start just with that. We need to draw this region. So let's see. We draw ourselves a nice xy axis. We have the x equals 0, that's the y-axis. Y equals 0, that's the x-axis. Y equals ln of x. I know at the very least that y equals ln of x goes through 1, 0. And below the x-axis, it heads down to negative infinity. And above the x-axis, it kind of almost looks like a square root function, but not quite. All right, so that's our shape there. And then we have the line y equals 2. That's a horizontal line going through y equals 2. And so I can draw that as well. There we go. So there's y equals 2. We have our y equals ln of x. And then we have the y-axis and we have the x-axis. So here's our shape. This is the region where this is our big D, okay? So that's the shape of our lamina. And what we want to do is integrate over that shape the density. Well, let's look and find the density. If the density of the plate at any point xy is x e to the y, okay, there it is. That's our density, rho of xy. And that's grams per centimeter squared. Find the mass of the plate. Okay. They say to assume the axes are marked in centimeters, and that works out well with the units that are being used for the density, being that they are grams per centimeter squared. Okay, so let's go ahead and calculate our mass. We have to set up our integral. We have our mass is equal to the double integral of our density, x e to the y, and now I have to figure out my bounds. It looks like, well, this is interesting. It looks like I should actually treat this like a type 2 region, and here's why. I have one left and one right. So I'm just going to draw these arrows to indicate that. The left is x is equal to 0. The right is, well, let's see. I need to convert my y equals ln of x. It becomes e to the y is equal to x. So that would be my right function. While y will go from 0 to 2. If I try to do a type 1 function, what's going to happen is I have two bottoms. I have the bottom that is the part of the x-axis down here. That's our y equals 0. But then I also have this part that's y equals ln of x. That's actually counting as a bottom. And so I'd have to use two integrals in order to evaluate this, and I really don't want to do it. So this, I'm going to make this a type 1. And what that means is that our inner integral will be x bounds. Okay, so we're going to go from x equals 0 to x equals e to the y. And when we do that, y is going from 0 up to 2. And so that means our order of the differentials will be dx dy. Okay, Now we can integrate. Remember, we are integrating with respect to x first. Y will be a constant or treated like a constant, so I'm just concerned about that x. And when I integrate that, I get 1/2 x squared. So this is the integral from 0 to 2 of 1/2 x squared e to the y. And we've got x going from 0 to e to the y. And then after we evaluate that, we can integrate with respect to y. All right, let's evaluate. This is equal to the integral from 0 to 2 of the evaluation at e to the y. I've got 1/2 e to the y all squared times e to the y, and then minus 1/2 times 0 squared e to the y dy. That second term's just going to go away. This e to the y all squared, when you have a power to a power, you multiply, so that becomes e to the 2y, and then times e to the y, and if you have the same base, then you add your exponents. So the way this simplifies is we'll get the integral from 0 to 2 of 1/2 e to the 3y dy. All right, so now I need to integrate e to the 3y, and that multiplier that's in the exponent, when I integrate, that'll become a divider. So this becomes 1/2 times 1/3 e to the 3y from 0 to 2. Evaluating it, let's pull this 1/6 out. We have e to the 3 times 2 minus e to the 3 times 0. And that gives me 1/6 times e to the 6th minus 1. And that's our final answer. That is the mass of that lamina that's shaped like that with the particular density we are given. Okay, so calculating mass is not too big of a deal. We just have to come up with a region. We need to know that density is what we're integrating, and then we go ahead and do it, just as we've been doing through the past 3 sections. So we have this other one, and here we're asked to find the mass of the lamina that occupies the region D and has the density function rho of xy is equal to x squared. So I've got my density function already here. All right, and D is the triangular region enclosed by the lines y equals x, y equals minus 2x plus 6, and x equals 0. I need to draw that. Okay. So I'm going to go ahead and get, let's see, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. Y equals x very nicely just bisects the the first quadrant. So I can draw it like that. It does also travel through the third quadrant. All right, the y equals minus 2x plus 6, that has a y-intercept at y equals 6. And then we have a slope of -2, so we'll go down 2 over 1. That gets us there. Down 2 over 1, that gets us here. We can connect these dots. That's pretty close. There we go. I can see an intersection point there and extend. X equals 0 is the y-axis. So this is the triangular region we're looking at. It would be really easy to get this region wrong if you thought x equals 0 is the x-axis. So be really careful about that. Our region is right here. This is big D. Okay. It looks to me like it would be easiest for us to handle this by treating this like a type 1. I've got a bottom for y equals x, that's the lower bound. And then I have a roof of the y equals -2x plus 6. And then during that time, x is going from 0 over to 2, because I can see my intersection point there very well. So I'm going to set up my mass using a type 1 region. Mass is equal to the double integral. My density function is just x squared. And I'm going to use x as my lower bound on my y integral. and I'm going to rewrite this as just 6 minus 2x for my upper bound. My lower bound for x is 0, and my upper bound for x is 2. So we're doing this dy dx. All right, when I integrate with respect to y, I have to remember that x squared is just a constant. And so this just becomes the integral from 0 to 2 of yx squared from x to 6 minus 2x. After we integrate that and evaluate that, we can integrate with respect to x. Everywhere there's a y, plug in the 6 minus 2x and then the x. So this gives me the integral from 0 to 2 of, I'm going to pull this x squared out. I have x squared times 6 minus 2x minus x squared times x. Okay, we need to distribute. Remember, where there is no product rule in integration, so you always have to multiply things out or do a u substitution. I'm going to multiply out. I get the integral from 0 to 2 of 6x squared minus 2x cubed minus x cubed dx. And I can combine those to get minus 3x cubed. So it's the integral from 0 to 2 of 6x squared minus 3x cubed dx. All right, one last integration. And antiderivative of 6x squared is going to be 6 over 3x cubed, and then minus 3 over 4x to the fourth. We're evaluating from 0 to 2. All right, that 6 over 3 is just a 2. And I'm going to evaluate it 2, and I get 2 cubed minus the 3/4 times 2 to the fourth. And then minus the evaluation at 0 is just going to give me 0 minus 0. So no contribution there at all. 2 cubed is 8, times 2 is 16. 2 to the fourth power is 16. So I get minus 3 times 16 over 4, just so we see it. The 4 goes into the 16 4 times, and 3 times 4 is 12. So I have 16 minus 12, which is a grand total of 4. Now here's something to make note of. When you are integrating and you're supposed to be finding mass, you better get a positive value. If you get a negative value, something is wrong, okay? It's kind of a key indicator that something went wrong. All right, so that's mass. Now, when it comes to the next topic, moments and center of mass, we have a bit more work to do. Now, our lamina has variable density, and that means that we can't expect the center of mass of the lamina to be in the exact center. You may be familiar with buildings like the Leaning Tower of Pisa. It's able to lean and not fall over because its center of mass is not quite where it should be. And that's based on the way it was built and the lay of the land and everything. But there are outside factors that affect where the center of mass is in any sort of lamina, whether that lamina be 2D, 3D, or whatever. So we need a way to calculate this center so that we could balance the lamina. So I'm showing a picture here of an oddly peanut-shaped lamina, and it is balancing on a sharp point. And there is no like true center that you would be able to point to, like on a circle, you know, the center. A peanut shape, it's like, well, I'm not sure how I could balance that, right? So we have to calculate that. The calculations are really tedious. So first we have to calculate the tendency of the lamina to rotate about the x-axis. So like, you know, wobbling sort of thing. And so that's the moment about the x-axis, and we call that m sub x. It's a moment about the x-axis. Notice that this looks very similar to the mass integral. The only difference is that we do y times the density. So the moment about the x-axis is y times the density, and then we integrate over the shape of the density still. Then we need to calculate the tendency of the lamina to rotate about the y-axis, and that'll be called the moment about the y-axis, so m sub y. And now it's different because we're going to be integrating x times the density function. And we'll integrate again over the shape of the lamina. Then once we know what those moments are, the moment about the x-axis and the moment about the y-axis, we can calculate the center of mass of the lamina. Those are the x bar and y bar. So x bar will be the moment about the y-axis divided by the mass, and y bar will be the moment about the x-axis divided by mass. These are formulas that I give you on your formula sheet, so there's no need to memorize them, but you do need to know how to calculate them and like what it is you're working with, okay? So we'll start right in with an example. We have a flat plate. It's in the shape of the region defined by the inequalities. X squared plus y squared is less than or equal to 4. 0 is less than or equal to y is less than or equal to 1. And x is less than or equal to 0. I'm going to draw that first. Okay, so let's see. X squared plus y squared is less than or equal to 4. That's a circle of radius 2 and everything included inside. But I'm also noticing, well, let me go ahead and draw that. So 1, 2, 1, 2. All right, so if I want to draw this, I've got my intercepts all at the 2's. And here's my circle. Okay, that's x squared plus y squared equals 4. And if I shade it all in, it's the less than or equal to 4. Okay, I'm not going to shade yet because they also tell me that y is only between 0 and 1 and x is negative. So that means we're looking at, so y is between 0 and 1 and x is negative. That means we've got this shape right here. And that's it. Kind of an odd shape. All right, so that's our lamina, that's its shape. And then we have the density of the plate at any point is negative xy. And in here, we're just being asked to set up the integrals to find the mass and the center of mass of the plate. And that is all I'm going to do here. It's a pretty straightforward integrand. But definitely work them out if you feel you need the practice. And I will give you the answers here as well. So when I set this up, I have 3 integrals that I need to calculate, because we need to find x bar, y bar, which we just learned is going to be the moment about the y-axis over the mass, that's the x bar, and the moment about the x-axis divided by the mass. All right, that means we need mass. Mass is going to be a double integral of negative xy. And now I need to figure out how I should handle this this region that we're dealing with here. Well, it looks like I should probably treat this like a type 2. And I'm looking at the leftmost side of that region, and it's like part of the arc of the circle. And I have the equation of the circle, so maybe I should just solve for x. And x squared plus y squared is less than or equal to 4. I want x is equal to the square root of 4 minus y squared, but it's not the positive square root because I'm on the negative x-axis. So this is the negative square root. That will be my leftmost function. My rightmost function is x equals 0. So my lower bound here is negative square root of 4 minus y squared up to 0. While y is just going from 0 to 1. So we'll do dx dy in order to find the mass. The mass, after much calculation, is going to be equal to 7/8. See how you do with that one, okay? You'll end up integrating with respect to x, and then you're going to plug in your bounds. And because when you integrate with respect to x, you end up with an x squared, it's going to take care of that square root and things will work out really nicely. All right, m sub y, that's another thing that we need. M sub y is equal to the same integral, but now we're going to take the density function and multiply it by x. So I have x times negative xy. My bounds are still the same, negative square root 4 minus y squared up to 0 and 0 to 1 for y. So we're doing dx dy. And this is going to be equal to Oh, I didn't actually calculate this out. I can give you the final x bar and y bar values when I get them. Okay, and then let's see, we have m sub y. Well, we can actually simplify this a little bit, just so I can talk about what the integration might look like. We have the integral from 0 to 1, integral negative square root 4 minus y squared up to 0 of negative x squared y dx dy. Okay, now when you integrate, you're going to get a cube, okay? And with that cube, we're going to plug in a square root. And so that whole 4 minus y squared is going to be under a square root and under a cube, which means it's raised to a 3/2 power. Okay, you'll need a u sub for dy. dx is no problem. It's the dy that will cause issues. And then m sub x will be equal to the exact same integral. There's only one change. So we'll still go from 0 to 1. We'll still go from negative square root of 4 minus y squared up to 0. But now it's y times the density function minus xy, dx dy. So I can just go ahead and rewrite that one more time and talk about the actual integration. We get the negative square root of 4 minus y squared up to 0. And our integrand now is negative xy squared dx dy. So now when I integrate first with respect to x, the x will end up being squared. And when I plug in that square root, they'll cancel each other out. And this one will actually work out really nice as well. And then in the end, in your final answer, is that x bar will be equal to m sub y divided by m. And since m will end up being 7/8, that means we're going to get 8/7 times m sub y, whatever that ends up being. And y bar will be m sub x over m, which will be again 8/7, but now times m sub x. Okay, so there's definitely a lot of work involved in calculating the integrals. And you do have the formulas, but you also do need to know how to work with those antiderivatives. So practice, 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 for sure. The next problem is another center of mass problem. And I think I wrote and instead of. Find the center of mass of the lamina. Okay, and we're just going to set up the integrals to calculate it. So again, the density at any point on a semicircular lamina is proportional to the distance from the center of the circle. So here I chose this example to focus on how do we come up with that density given the way they gave it to us. We need to translate this sentence. The density at any point on a semicircular lamina is proportional to the distance from the center of the circle. First, we need to draw a semicircle. We can assume that the semicircle is the top half, and we do not have an actual radius for our semicircle. This is completely arbitrary. So let's also define this. We're going to let, how about A be, I'll put that in quotes, be the radius of the semicircle. Okay, so I'm going to go out by A units, and then I'm going to draw a really terrible semicircle, but it is one nevertheless. That's fine. Okay, so this semicircle has an equation of x squared plus y squared is equal to a squared. Okay, now the density at any point on the semicircular lamina. So I can just pick a random point. I'm going to go ahead and just pick a point right here. We'll call this xy. the density at any point on a semicircular lamina is proportional to the distance from the center of the circle. Okay, so what they're saying is the density, rho of xy, is proportional. That means equals k. When they just give you proportional, you can assume that means directly proportional. They would say inversely proportional if that's what they meant. Okay, so we're going to assume directly proportional. So that means that your density is not equal to the distance. It's equal to the distance up to some constant multiplier. So k. And the distance from the center of the circle, let's see, center of the circle would be at 0, 0. Well, let's see, we can, real quick, let's define distance. D is equal to the square root of x minus 0 all squared plus y minus 0 all squared, which simplifies to be the square root of x squared plus y squared. So that's the distance function, and that means that since our density function is proportional to the distance from the center of the circle, then we replace d with the square root of x squared plus y squared. Okay. Our region of integration is circular. And what this implies is that we should use polar coordinates. Now, you may be thinking that the last example had a circular region, but let's look back at that really quick. The last one had a circle as part of the definition, but the actual region was not a circle. It was rectangular with one slightly curvy side. That's it. So polar would not have been good for us there. But polar will be good here because we're trying to integrate over this whole semicircle. Okay? So we're going to use polar coordinates. And since it's a semicircle, what that means, circle, that gives us some information about r and about theta. For r, remember, r is always positive, so it starts at 0, and then we're going to go out to the max radius, which is a. And then theta, since it's a semicircle, well, just in the top half of the circle, that means theta is going to go from 0 up to pi. Okay? And then our integrand, we have k square root of x squared plus y squared. We have to always remember that x squared plus y squared is r squared. So we're looking at k square root of r squared, which simplifies to be kr. Okay? And then dA, we have to always remember is r dr d theta or r d theta dr, depending on what order we want to go. All right, let's go ahead and do this. So the mass is going to equal the double integral of kr. That's going to be our density function. And then we need to decide if we're going to do dr first or d theta first. It doesn't really matter. I'll go ahead and do r first. So r will go from 0 to a, theta will go from 0 to pi, and then we're doing r dr d theta. I rewrite this. I get 0 to pi, 0 to a of kr squared dr d theta. Okay. Now, if I was to work this all out, it's not a difficult one. This is a very simple integral to work through, and at the end, my answer will be in terms of k and a. I'll end up with k a cubed pi over 3. All right, so that's mass, but we want center of mass, so we need the moment about x and the moment about y. The moment about x, well, before we even do that, we have to remember x is equal to r cosine of theta. and y is equal to r sine of theta. So remember that in the moment about x, we put in a y multiplier. And so instead of that y multiplier, I now need to put in an r sine theta multiplier, right? So in m sub x, we need this for y. And over here in m sub y, we need this for x, okay? Now, I'm going to set up my m sub x. It's equal to the double integral from 0 to pi, 0 to a of, well, our density was kr, okay? So I've got my kr in there. And then we have that multiplier. We're multiplying by y, and y is equal to r sine theta. So we have times r sine theta. And then we have our differential dA, which is r dr d theta. So there's a lot of r's in there, and it's really easy to lose one of them or suddenly end up with too many. If you have 3 r's showing up, it's r cubed. So let's just rewrite this with the integral from 0 to pi, the integral from 0 to a of kr cubed sine of theta dr d theta. Okay, now that one you're going to integrate with respect to r. It's just a polynomial. That shouldn't be too big of a deal. And then with theta, you just have a sine of theta to integrate. So that one shouldn't be bad either. M sub y will be very similar. Same bounds, 0 to pi, 0 to a. And then our density function was kr. We have to, since it's the moment about the y-axis, we need to multiply by x. But x is r cosine of theta. That takes care of my x. Then we have dA, which is r dr d theta. I'll rewrite that one more time. 0 to pi, 0 to a of kr cubed cosine of theta dr d theta. All right, so you would calculate these 3 integrals, and then finally you would have that x bar would be equal to m sub y over m, and y bar would be equal to m sub x over m. Okay, so the moment about y over the mass and the moment about x over the mass. It's a lot of calculation. There's a lot of room for error. It's a bit tedious. You'll have 1 on an evaluation, but you won't have 7. All right, but you should be comfortable after the homework with setting up your own density function, given that maybe they give it to you or maybe they make you build it. Now that k value that's in here, that is only there because this was one of those proportional problems where they told us that the density is proportional to something, right? If, like, for example, in the previous problem, they didn't do that. They gave us a function that modeled the density. It was minus xy. So I didn't throw a k in there just for jokes. Like, there was no proportionality problem. I bring that up because I see it all the time. People get used to writing the k in there, and then they think it's part of the mass in the center of mass formula. And it's not. It's part of building an equation when you've been told that there's a proportionality situation going on. All right, so that's mass and center of mass when you're working with a lamina that has a variable density. That is the conclusion of 15.4. Please reach out if you have any questions.